Afternoon, everyone. Welcome to this afternoon tutorial session. In this one, we'll be giving Paresh a chance to talk to you about segment routing. And I think it should be fun. Thank you so much. Enjoy.
Thanks a lot, Mark. I presume all of you can hear me all right. You're welcome to come to the middle of the room. Just saves my neck a bit here. But if not, that's okay. That's okay. All right. So today, what this session is about is segment routing, as its title suggests. Now, before I normally get started off with any tutorial, I try to get a sort of sense of the room and what people actually already know about segment routing. So anyone here who's worked with segment routing or is familiar with segment routing? Warren. Okay, so we've got one. How many of you have heard of segment routing? Most of you. Okay, good. So obviously, whatever you've heard about segment routing has piqued your interest enough for you to come and join this session. So this is awesome. So very quickly about myself. So my name's Paresh Khatri. I actually work for Nokia. In my current role, I'm the CTO for the IP Networks Group for the Asia Pacific region. I am based in Brisbane, and I've been running this tutorial for a few years now. It's 7 or 8 years, I think. The first time I ran it was probably at the Apricot that was in Ho Chi Minh City. When was that? Anyone know? Okay, it's lost in the mists. 2017. Okay, all right. So 2017 or 16. Okay. So it's about 6 or 7 years that I've been running this tutorial. Okay, so I've got a lot of material to cover today. Segment routing is a big topic. So the agenda is actually quite simple. The first half, which I guess which is the first 90 minutes, I hope to spend on describing the basics of segment routing, the protocol mechanics, the problem that we're trying to solve here, and so on. I will have a few examples there. But in the second half, when we come back after the break, I hope to look at some of the use cases to see segment routing in operation, some of the different scenarios in which we use segment routing. We look at some deployment options. How do people go about deploying segment routing? How do you migrate from your existing protocols to segment routing? Or indeed, how do you actually interoperate with the existing protocols that you have in your network? And then there's a section on IGP extensions for segment routing, which we will not be touching on. This is just purely for your reference. The slides should be up on the website. I mean, if they're not, they should be coming pretty soon because I did upload the latest copy of them just an hour ago or so. So it should not be too long before it appears on the Apricot 2023 web page. Okay, so like I said, there's a lot of content here, and typically, depending on the audience and the level of interaction I get and so on, the length of the presentation varies. Now, we've got two 90-minute slots, so we've got 180 minutes to play with. So that's not really going to change, but what's going to change is how much we cover in that period. So the way I intend to do this is I'll keep going until we hit that end of the second session, and then I'll stop. And it's okay, because the later part of it is all about different use cases. So even if you miss out on a few of them, you've got the reference slides, and we can have a chat offline as well. Okay, so one final question that I wanted to ask before well, a couple of other questions I just wanted to ask here. How many of you are familiar with MPLS and or operate MPLS networks? Oh, so quite a few of you. Fantastic. This is great. It makes our life a lot easier, and it gives you a reference point for comparing segment routing with MPLS. Last question, I promise. How many of you work for operators? Once again, quite a few. Fantastic. So we've got I think we've got the right mix of prior experience plus the target audience for this. It's a tutorial. I'll be talking a lot, but I would like to get a break every now and then, so I'll ask you some questions. Alternatively, if you have any questions at all, raise your hand or call out as we go along. I think it's more fun, more interactive, and well, someone's already leaving, so obviously it's okay. Wrong place. Okay, good. I will not take it personally then. No. So in order to make it more relevant to you, please raise your hands. I'm here to answer any of your questions. So let's get straight into it. The basic elements of segment routing. Now, before we can talk about segment routing, I think it's important to look at the drivers for segment routing, and some of the motivations that we have for actually thinking about the whole concept of segment routing. Now, when it comes to MPLS, we've got a long history with MPLS. Operators have been deploying MPLS for 20 odd years now. Like, it started early 2000s. At least my experience, the first time I touched MPLS was, I think, 2002 or 2001 or something like that. Back in the very old days when we were still running ATM and trying to come out of that environment. So two protocols really came to the fore as part of the development of MPLS. There's LDP, or the Label Distribution Protocol, and there's RSVPTE, which is your Resource Reservation Protocol, extended for traffic engineering. Now, each of these protocols has its place in the MPLS architecture. The LDP protocol is one that is used because it's essentially quite simple. It gives you MPLS. It's very simple to operate, and from a configuration perspective, it's very light. You don't have to do a lot to get LDP up and running. Over the years, we've extended LDP with a lot of other things, like multicast LDP. We've introduced things like fast reroute into LDP with something called loop-free alternates, or LFAs. So it's become a really good protocol. Now, we also have RSVPTE, as I said, and the applicability for RSVPTE for a long time has been to provide traffic engineered services, to do some sort of traffic engineering, avoid certain paths, or use certain paths, or optimize for certain outcomes in your network. Now that's something that LDP could not really do, so we turned to RSVPTE. And for a long time, the only way of doing fast reroute was to use RSVPTE until LDP LFA came along. So a lot of operators deployed RSVPTE for fast reroute purposes as well. So as we went along, once again, we found that we hit some challenges with how these protocols were scaling in the network. So we did, we came up with nice architectures to get around these scaling challenges. We did things like tunneling LDP over RSVPTE, right? So you could have, for example, a core network running RSVPTE, and then you've got the edge networks, the aggregation networks connecting into it through LDP and running LDP within those aggregation networks. And operators found that there was a nice compromise. You controlled through traffic engineering your capabilities, your routing in the core of the network, which is where you're handling the most amount of bandwidth. And for the rest of the network, we used LDP. So that's worked reasonably well. We also brought in things like seamless MPLS. For those of you who are familiar with that, it's a hierarchical construct where you've got two layers of MPLS. You've got firstly BGP-LU, or labeled BGP, RFC 3107 kind of construct, and underneath that you've got the transport layer, which can be running LDP, can be running RSVPTE, and so on. The primary reason for doing that was to really scale MPLS to very large networks. Right. So once again, today's seamless MPLS very widely deployed around the world, and it does a pretty good job. So traffic engineering, like I said, was predominantly RSVPTE. We don't really have too many other options, and we built this service infrastructure. And when I say services, I mean the VPN services such as your virtual private wire service or your virtual private LAN service, or your IP VPN services, right? So we build constructs to allow those services to be carried over an MPLS network that is using, any of this seamless MPLS, LDP, RSVPTE, and so on. So we've invested a lot into making that work. Now, where we are today, we find that there are some challenges. I mentioned them already. The challenge of scaling MPLS has been, quite significant, and we've invested a lot in making that happen. But as we now look at the traffic demands on networks, we find that there's a requirement by operators to do traffic engineering on a more granular basis, potentially even a per flow kind of traffic engineering, to be able to do things on demand, in a different manner, in a differentiated manner for different types of services. So the scaling challenge that we have with MPLS gets compounded because, now you're adding a completely different element to it. You need way more tunnels and so on. So that's a challenge. On the LDP side, the provision of things like fast reroute, it's a bit more complex. It's not, there are topology dependencies on the ability to achieve fast reroute in networks that are running LDP. So that becomes a bit more complex. So looking at that now, if you summarize these two protocols, LDP is a multi-point-to-point construct. What it means is that you could use the same label from multiple points or multiple sources of traffic to converge onto a single sink or destination, right? So it's like a tree-like structure that we have with LDP. So it's just considered a multi-point-to-point construct, which is good. It's efficient. RSVPTE, on the other hand, is purely a point-to-point construct. So for every pair of points in your network that need to communicate with each other, you need to have an RSVPT tunnel. From an operational perspective, LDP very simple, RSVPTE not so. Like I said, every pair of devices or provider edge devices that need to communicate need to have a tunnel that is actually set up beforehand. Now, from a dependency perspective, LDP relies on the IGP, which is fine, right? It gives you the shortest path first kind of forwarding. RSVPTE does rely on IGP for things like distributing traffic engineering information through the IGP. Now, from a label allocation perspective, they're all fairly similar. Labels are locally significant. That's pretty much all we've known when it comes to unicast MPLS forwarding in networks. Labels are locally significant. What that means is that at every hop, the label changes. We're used to that, right? We run MPLS networks. We know how that actually works. Traffic engineering, as I said, LDP does not support it. RSVPTE does, right? So there's a clear differentiator here. Scaling, LDP scales pretty well because it does not have the concept of these signaled tunnels, and it's got this multi-point-to-point traffic forwarding paradigm. Whereas with RSVPTE, you run into the n-squared problem. You've got to create a mesh. Every pair needs to set up a tunnel between them. Fast reroute, I've already talked about. LDP, you have loop-free alternates. You don't always get 100% coverage. What that means is that there are certain scenarios where you cannot protect a link because the LFA algorithm cannot guarantee the fact that it's loop-free, right? It's somewhat conservative. It's not going to send a packet on a path if there's any chance of it being looped back. So you don't get that. RSVPTE, a bit better. You can actually do it. Multicast extensions for both of them. IPv6 supported on both of them. Not many operators have deployed MPLS networks with an IPv6 control plane. There's very few number in the world that have done it, but the capabilities do exist. So these protocols are actually quite different in that way. So that brings me to, what problem are we trying to solve? I've already alluded to some of these things. The problem of scale, to get granular traffic engineering in a network. And by granular, I mean potentially down to a per flow traffic differentiation. RSVPTE is really the only solution we've had to provide traffic engineering in our transport networks. There's no such thing as LDPTE. Now, before someone corrects me, there was something called constraint routed LDP, CR-LDP. It never really, it got specified and so on. No one actually implemented it. So let's not include that as a valid option. LDP fast route, as I said, can be used in some parts of the network, but it's dependent on the topology to work well. Now, RSVTE, some pros. It's a source routed protocol. And this is where we're starting to get into the whole concept of segment routing in a way. Source routed, it means that the source of the traffic determines the path that is taken on its way to the destination, which is obviously very different to your normal longest prefix to lookup hop by hop routing in an IP network otherwise. RSVTE has very strong fast reroute and traffic engineering capabilities. The cons of that, quite a few cons, right? The sheer number of tunnels means that you have a problem, firstly, from a configuration perspective, because all of these have to be configured. These tunnels between every endpoint in the network have to be configured. There's this problem with state as well. RSVTE has or uses something that we call soft state. So what is soft state? Soft state means that it's state that is instantiated in a network, and that is valid for a period of time unless it's refreshed. So if it's not refreshed, the state could disappear. It'll be torn down. So in order to make sure that the state is kept up, RSVTE has to keep sending these path and RSV messages all the time. So there can be a lot of signaling. Now, we've got some solutions around refresh reduction and so on that help somewhat with that. But it doesn't reduce the amount of state. So you find that in the middle of, or in the core of these RSVTE networks, you have this concentration of LSPs. And look at your scaling guides for your platforms, and you'll find that if it's a reasonably large network, you will hit some of these limits. Now, the more state you have, the more memory you'll consume, the more control plane traffic, the more CPU cycles you'll burn when things go wrong and you have to reroute and so on. So that's not necessarily a good thing. So that's the problem we actually set out to solve here with segment routing. So the primary objective for segment routing, now this is straight from the IETF. This is source routing. So source routing is really the ability for a node, which is your ingress node typically, to specify a unicast. So once again, I'll emphasize this is unicast forwarding path that is not necessarily the same as the shortest path that a packet will traverse on its way to the destination. So what's the definition of traffic engineering? When you take in an IP network or an MPLS network, it's really when you take a path that is not the shortest path. You want to influence the path to take some other, or you want to influence the packet to take a path that is different to the shortest path. So you're doing traffic engineering. So you want to have that ability for the packet to take this other path, but with a very key constraint here. The constraint here was that this technology should not require us to have state in the midpoints of the network. So we're sending traffic from node A to node Z in the network, and it's passing through nodes B, C, D, and so on. The only nodes that have to have state are the two nodes at the edge or the endpoints of this flow. You don't want any of the other nodes in the network to have any state, right? Like RSVPT. And as I mentioned, RSVPT suffers from the problems of a lot of state, lots of refresh messages, and just coping with that as the number of tunnels in your network grows. So the IETF then set up this working group, and it still exists. So you're welcome to go in and have a look at at what the Spring working group does. So Spring stands for source packet routing in networking. It's a bit of a stretch. That's how the IETF normally does. You've got some nice names that have come about as a result of some creative thinking. So the Spring working group in the IETF addresses this. It basically had this charter that said we want this protocol that allows you a number of things. one of those things is to have these very simple IGP-based MPLS tunnels. So instead of using a signaling protocol, can we extend the IGP to carry that label information, for example? And so the first use case is, your shortest path first, something you're doing all the time. So to tunnel services from a provider edge router to another provider edge router over the shortest path without having any state. Okay, so that's one very simple use case, and we'll see how that actually works. The second one was around fast reroute. So we want to do all that, but we don't want to lose the capability to do fast reroute. So this is important. And the requirement here for segment routing was that we should be able to achieve fast reroute without dependence on the topology. So if you recall, I mentioned that with LDP, the challenge we have is that there are certain topologies where you will not be able to find loop-free alternate paths because you cannot guarantee that loop-free attribute for it. So fast reroute has to be supported. And there's also a desire for us to be able to support a number of different types of constraints, things around shared risk link groups, to be able to do things like link and node protection, to do micro loop avoidance, when traffic is converging around failures and so on. There's a few other things. So traffic engineering, I've already kind of mentioned that. The soft state nature of RSVPTE causes it to experience a number of scaling issues. So we had to get around that whole concept of state in the midpoints. There's also a requirement that we should be able to get most of the functionality that we already enjoy with RSVPTE, right? So things such as having loose and strict options when specifying a path, to be able to do centralized path computation, but also distributed path computation and all these other features that you take for granted with RSVPTE. We don't want to lose this. And a very key requirement, which is there for a lot of new protocols that are being developed by the IETF, is that we should be able to introduce this into existing networks with just incremental deployment. It should not require a flag day, right? So you should be able to take an existing network and be able to upgrade it so that you can run segment routing on it. Now, segment routing sort of achieves that, but there are some challenges, right? So when you look at the operational considerations, you'll see that it's not always straightforward to achieve that requirement. Okay. The Spring Working Group mandated that the segment routing work should support 2 data planes. So the first data plane was the MPLS data plane, right? What do we mean by the MPLS data plane? Anyone? When we say to use an MPLS data plane, what does that mean? It simply means that we are forwarding MPLS packets. That's what it means. So we should be able to use the same mechanisms that are used by today's MPLS networks in order to forward this traffic. So that the header is the MPLS header. The label is the MPLS label. We're doing things like pop, push, swap, same things we do with MPLS. And this made sense, right? Because it means that we can use a lot of the existing forwarding infrastructure that operators have. You could run this on your existing hardware. Your hardware already knows how to forward MPLS, right? I've been doing this for 20 years. So if we had a segment routing control plane that resulted in these MPLS packets, then I think you're on a winner here, right? Because you're reusing the infrastructure that you already have. So that was one. The second one was to leverage the IPv6 data plane. Now, this is the whole concept of SRv6, which I'm sure a lot of you have heard of as well. Now, unlike MPLS, the forwarding plane for SRv6 is actually quite disruptive. To support SRv6, we had to develop a completely new routing extension header. We call it the SRH, right? Which is a segment routing header. It's an extension header for IPv6. So In the rest of this presentation, I'll be focusing on MPLS for a few reasons. It's easier to depict MPLS labels compared to IPv6 addresses. So maybe laziness on my part. But what I want to emphasize is that the thing here that's of interest is the mechanics for you to understand how things work in segment routing. Now, whether you end up going MPLS, SR-MPLS, or you go SRv6, the fundamental concepts of that are still very much similar in terms of how we forward traffic in networks. So we'll do MPLS. Okay. Now, I do apologize. There's a bit of terminology here. You know, when you're learning any new technology, you have to come to grips with the terminology. I'll try and make it easier with lots of diagrams and things, but ultimately you do have to learn some of this before the rest of it will make sense. So, you know, I've tried doing this material in different orders, but I find that, you know, it's complicated, and until you have the grasp of some of these concepts, it's a bit hard to understand the mechanics of and the operations of how this works. So stay with me. If you have any questions, just put your hand up. Okay, so what is segment routing? It's essentially a tunneling mechanism, right? It's a tunneling mechanism where you can take traffic that's coming in to an ingress provider edge and tunnel it to the destination, the egress provider edge device. And you can tunnel it through, you know, via a shortest path. You can tunnel it via a traffic engineered path and so on. But ultimately, it's a tunneling mechanism. Now, the path, if you recall, I said that the path that a packet takes in an MPLS or sorry, let me step back. The path that a packet takes in a segment routed network is dictated by the ingress provider edge. So the ingress provider edge, when it sends this packet out into the network, puts some information in the packet that dictates how the packet will be routed in the network, right? So it's not the core of the network, the P routers and so on that are determining the path. It's the ingress provider edge. And that's a very important concept. And the way it does it is by encoding the path information into the packet itself, right? Now think about this. It's a very powerful concept. For those of you who have used RSVPTE LSP, who's used RSVPTE here? Apart from Warren. Anyone use RSVPTE in your network? Yes, that's yes. Anyone else from here? Anyone from here? You haven't used RSVPTE. Okay. So let me explain how this works. So when you set up an RSVPTE tunnel in the network, it's signaled from end to end along a certain path. The entire path, or every router along the path, has awareness of the tunnel. It knows about, you know, every tunnel that's in the network. So when a packet is sent into the tunnel, each of these routers, by virtue of the fact that they know what the tunnel is, will be able to route along that tunnel. They'll make sure that the packet that enters the tunnel exits the tunnel on the other end, going through the path that was specified by the ingress. So they have to have awareness of that. Now, what we do in segment routing is completely different. Instead of the intermediate nodes having visibility of the path is in the packet. So the packet, as it reaches every point, every hop, is telling the network what to do with it. So this is how we can get rid of state. So we took the state out of the network and put it in the packet, in a way. Does it make sense? Right. So that's how we can get rid of the state in the network itself. So encoding that information into the packet is very important. Okay, so what is a segment? Why do we call it segment routing? Anyone? Take a guess. What does segmentation mean? Segregation. Not quite. Segmentation. Anyone else? When you segment something, what are you doing? You're taking something big chopping it, right, into little segments. We used to do that in the ATM world, showing my age once again. Segmentation and reassembly. Essentially, you could call it fragmentation in an IP world, right? But segmentation means breaking something down into smaller chunks, essentially. So what we do in a segment routing network is we segment a network into small chunks. And these segments, from a routing perspective, are what I call topological segments, right? If you had to send a packet from one router to another along a certain path, what information do you need? What do you have to tell the network if you want to send that packet from R1 here to R4 along a certain path? What do you tell the network? The next hops, right? So you might want to say, can you see my cursor? Yeah, you can. You might want to say, hey, I want to go to R2. And then from R2, I want to go to R5. And then R6, R3, R4. So instead of taking the shortest path, you wanted to take this longer path, for example. So you have to tell the network what path to take. And the way we tell the network what path to take is by encoding that path information as segments. There are really two key segments that are important. There are many others, but I'm trying to abstract this here, right? There are two things that are important from a topological perspective. It's nodes, which nodes we traverse, and which links we traverse, right? So if you could specify completely for a packet, say, hey, you come into the provider edge router, I want you to take this interface to get to node 2. When you're node 2, I want you to take that interface 3 to go to node 5. When you get node 5, I want you to take interface X to go to node 6 and so on. So you could specify in detail what path a packet takes through the network, right? So we call these segments. So if you look at this network here, each of the routers is a segment. Each of the links is a segment. Does that make sense? So we've divided this very complex entity called a network into a smaller thing called a segment. Sorry? Exactly. That's a good question. Yeah. So yeah, a broadcast domain can be considered a segment as well. Yes. It's just, yeah, a segment that is not a point-to-point segment in this case here. Yeah. So that's a good question. So we split this network up into these segments. Now, when we do that, the next step is we have to identify the segment somehow. So we assign an identifier to the segment. We call it a segment identifier, right? No brainer, right? That's a simple term. A segment identifier is also called a SID, an SID, right? So we have a number of segments in the network. We give them a name so that we can really tell the network what to do with every single packet that we want to send through it. Okay, so now we've got the concept of segments, segment identifiers, and paths in the network clear in our head, I hope. And if it's not, let me know. I'll repeat it. So remember I said that segment routing is a way of tunneling traffic. You tunnel traffic from the source to the destination. How do you tunnel traffic? In an MPLS data plane, basically what you're doing is you're putting a stack of labels. So people who work with MPLS, you know, you can have more than one label, right? We call it an MPLS label stack. There's no theoretical limit to how many labels you can have on a packet. Of course, there are lots of practical limits there, but you know, theoretically, you can just stack on labels as you choose. So in an MPLS network, when using segment routing MPLS, we encode the SID into a label value, right? So each of these labels will have a SID in it, and each SID will either be a node SID or an adjacency or a link kind of SID. Make sense? Now, in an IPv6 world, there's no such thing as IPv6 address stacking. So we came up with this segment routing header, the SRH. And the difference there is instead of having a stack of MPLS labels, we have a set of IPv6 addresses that are designated as SIDs that are in the segment routing header. but the process is conceptually the same, whether it's a stack of MPLS labels or a set of IPv6 addresses. Okay, so like I said, the segment list then represents a path, which is made up of topological entities, nodes or links. So you can see here an example, a packet with 4 labels that are on it as part of their stack. Now, one good way of thinking about a segment identifier, or a segment, I guess, is that it's an instruction. A segment is an instruction to the network on how to forward the packet next. So we put it there. Think of it as an instruction. It actually helps you to think about this. And instruction can have different semantics or meanings. If it's a SID for a node, the instruction there is route the packet using the shortest path to this node. That's the instruction. If it's an adjacency SID, then it's an instruction that says, send the packet out of this interface, regardless of shortest path first or anything. Just put it out on this interface, right? So they're different SIDs that have different semantics. Now, just like we have with MPLS, we have operations on segments. So the operations that we have on segments are very similar. Now, can anyone tell me what are the 3 key operations in an MPLS network? Push. Yep. PHP. Swap. Yeah. Right. Brilliant. Okay. So the key ones here are push, pop, and swap. PHP will come to a little bit later if you haven't come across that. It stands for penultimate hop, and just a bit of added complexity that we don't really need, but we will talk about this. So the push operation in an MPLS network is about adding a label to an additional label to a packet, right? It may be a packet that is already labeled and you're adding a new label, or it could be a packet that is a native packet that does not have any MPLS label and you're imposing the first label on it. Doesn't really matter. The net effect of a push is that you end up with more labels than you had before. We then have the swap operation, which is basically taking the top label and swapping it for another label, right? So the number of labels doesn't change as a result of the swap operation. And then you've got the pop operation. The pop operation removes labels from an MPLS label stack. It could be 1 label or 2 labels, it doesn't matter, but it's kind of, you end up with less labels than when you started off. Now, in a segment routed MPLS network, we have similar operations, except we have different names. And we have different names because these names are generic across segment routing MPLS and SRv6, right? So one operation is the push operation, exactly the same, right? You're adding a new segment to the top of the segment list. The next operation is analogous to the pop operation. So next is you're done. You're done with the top label. Take it out, put another one in. Oh, sorry. Take it out and forward based on the next label. And then there's a continue label, which is exactly the same as the swap. Continue means we're not quite done yet. Look at this label, swap it, and then carry on. So the active segment is not completed. That means, right? So you end up with the same label. So push, next, and continue. 3 operations. So with the MPLS instantiation of segment routing, which you call SR-MPLS, we encode the SID in the MPLS label field. Now, the MPLS label field is how many bits? It's right there, guys. Okay, it's an open book exam, this one, right? It's 20 bits, right? A SID technically is 32 bits. So what we do is in an MPLS network, we constrain the SID to be 20 bits so they can fit inside a MPLS label. That's just a little bit of detail. It's not really important. But the essential point here is that in an MPLS network, the SID is encoded within 20 bits in the MPLS label stack entry. Okay. So now, when we run segment routing over MPLS, the operations are as follows, right? We represent a list of segments as a stack of labels, right? So put it on the label header. The active segment, now that's an important concept. In MPLS networks, we talk about the top label. Top label is the one that we are acting on at any point in time. So in a SR MPLS instantiation, we talk about the active segment is the one we're looking at. The continue operation, as we said, is swap, next is pop, and push is push. So I've already spoken about that. Okay, so like I said, there's a bit of theory to grasp here. I promise you it'll make sense as we go on. So just trust me on this. A few more slides. Now, in segment routing, unlike what we do with unicast, LDP, and RSVPTE, we have the potential to use global labels or globally significant labels. This is a big departure from what we had or what we have with LDP and RSVPTE, where in such a network, your label changes at every hop. But with segment routing, we use a globally significant label range. And this label range is something we call a segment routing global block. So what we do is the MPLS label space is 20 bits, right? So it's 0 to 104.48.575. So just over 1 million labels. What we do is we carve out a portion of that label space and say, hey, we're going to use it as our globally significant label space for segment routing. And we call it the SR global block. Okay. Now this is configured on every node that is participating in the segment routing domain. Now, it kind of goes without saying, but I'll say it anyway. It makes sense if you use the same sRGB range on every node in your network. It just makes life a lot easier if all of the nodes in the network have the same sRGB. Now, this may not be possible all the time, but I will not say much more about it until a little bit later when you have more of a grasp of it. But for now, good practice, we want to have the same sRGB range on every node in our network. Okay, so a bit more theory. I might go through this a little bit quicker. So types of segments. What are the two types of segments I've described so far? Ipeli, what are the two types of segments? That's the two data planes, yeah? But what are the two types of segments in a network? Topological things. Nodes and links, right? Fantastic. So we've got nodes and we've got links, right? So a good way to look at this is taxonomy, which I've got here. So there's a set of segments that are associated with information that is advertised by the IGP, right? We call it IGP segments. So what sort of information does an IGP typically advertise? You've got prefixes, right? So you can have segments that are associated with specific IP prefixes that are advertised by a IGP. You could have a further division of that. Like a prefix could be something that is associated with a node. So for example, a loopback address or a system address for a node, right? That's a /32 or a /128, depending on what you're using. It could be an anycast segment. But essentially, this is information that is, that identifies a node in the network. And then you've got adjacency segments, right? These are the ones associated with the links. We call them adjacency segments. Now, we'll also have BGP segments. So just like the IGP segments, we've got segments that are associated with information that is advertised by BGP or associated with BGP. So there's a few of them. Firstly, you've got prefix segments. So this is now associated with prefix information advertised by BGP. And there's egress peer engineering segments. So prefix segments are very similar to your node segments and anycast segments, right? So essentially, a BGP prefix and a SID associated with that. And then you've got egress peer engineering segments. Now we've got an example later on where this will make sense. There's three different types. There is a segment that identifies a BGP peer, the node itself. There's a segment that identifies an adjacency to a BGP peer, right? The link to the BGP peer. And there's also this other concept called a peer set segment, where you could be using, you could have, a number of peers that are part of a peer set. This will make more sense when I go to the example, but just trust me on this. Okay, so these are different types of segments. So I'm going to skip this slide here and go into this. Okay, so looking at all of these different slides or different types of SIDs that we have in the network. So prefix segments. Remember, these are segments that are associated with routes or prefixes that are advertised by the IGP. They will generally be globally unique within the domain. And when we say globally unique, what do we mean? They will have a globally significant label when using an MPLS data plane, right? So a globally significant label that identifies a node. The semantic of that, remember I mentioned that. What does it actually mean? When a node in the network sees one of these, what does it actually mean? It simply means that it's an instruction to that node to send traffic or that packet via the shortest path to the node that is associated with that label. Okay, so take the shortest path. Typically, there'll be multiple hops between your edge and edge devices. So like I said, there's a bit of complexity here, which I'll come back to a bit later, which is around indexing. Now, when we had this segment routing global block that I described, I said that it makes sense for every node in the network to have the same segment routing global block, because that means that you can allocate globally significant labels that every router in the network understands, because it's from the same range. When you have a different range, that becomes a problem. But we don't want segment routing to stop working. So we cater for that by using this concept of indexing. We'll come back to it. So don't stress too much about this right now. Right. So that's a prefix segment. Now, a node segment is a prefix segment. It has the additional attribute that the node segment is used to identify a router in the network. Right. So like I said, it's typically associated with some sort of loopback address or a system address that identifies a router. When we advertise it, there's a flag. Once again, don't worry about it unless you're doing packet captures. And the semantic here is that route me using the shortest path to this destination. So same semantic as obviously your prefix segments, because this is a prefix segment. Now, you also have anycast segments. Anycast segments, it's okay. Let me maybe ask you a question. So when we use an anycast segment, you give the same IP address to multiple devices, right? Essentially. So how would this play out in a segment routing network? If you had a few nodes as part of an anycast set, what could you say about the node set for these devices? It'll be the same. So instead of having, just like we have the same anycast IP address for a number of devices, you could use the same anycast SID for a number of devices. So it's simple as that. Instead of using an address, you're using a SID. Okay, so let's finally get into an example. And this is where I will try and put some of these things together, try and join the dots, so to speak. So we have this scenario here where we've got a very simple network. You've got provider edge routers, 2 provider edge routers going through 3 provider routers in your network. So the way this works is you go in, you've turned on segment routing, and you're really happy because there's this good stuff. What happens? What happens in the network? So we're gonna look at this from the perspective of traffic flow from left to right, right? If traffic flow is from left to right, the control plane flow has to be from right to left, obviously, right? That's how it works, the MPLS network. You advertise information this way and traffic goes the other way. So what we do is we go into the router, and just like you configure an IP address for a box, for a router, you configure a SID for the box. I haven't gone into the details of the segment routing global block. Remember, I said the SID has to come from the segment routing global block, but I will later on. Assume that on this node here, you set aside labels from label 500 to 1000 as segment routing global block, and you picked 800 to assign to this router. So you picked a label from within the segment routing global block of 800. So what happens here? Like I said, what the Spring Working Group set out to do was to eliminate some of these protocols that we currently use for MPLS. Now, when using LDP, that label would have been advertised by LDP. In segment routing, it's not LDP. What we do is we enable the segment routing extensions for the IGP. So OSPF, ISI is both supported. So when we configure this, it's advertised as part of your IGP, LSAs or LSPs, depending on what you're using. So 800 will now be advertised. So let's see what happens in terms of how the traffic or the control plane actually works. Now, in a MPLS router, we've got this thing that we can call a label forwarding information base, an LFIB. So a bit like your FIB, your routing FIB, except it's a label FIB. So it's dealing with label information. And the LFIB is actually quite simple. It's got, it's got a I guess one column, which is the incoming label, and the other, and one column that's the outgoing label plus information about the next hop. Okay. So when a MPLS packet comes into a router, it looks in the LFIB. Goes, okay, a packet comes with a label of 100. It'll go, shh, this is a 100. What do I do with it? And some of the options for what we can do with the packet with a certain label are: we can pop, we can push, we can swap. Right. So this is how MPLS operations actually work. So now what we understand is that these tables have to be built somehow, right? So there's some protocol mechanics that's happening in order to build the tables. So I'll go through how this table is built. So node SID 800 was advertised by PE2 in the IGP. So what happens is it'll be received by all of the devices, all of the routers in the network. So P3 receives that information, right, in the IGP advertisement. And by virtue of that, it learns that, okay, the globally significant SID for PE2, the node SID for PE2 is 800. So what I've got to do is I've got to create an entry here that says, if I receive anything with a packet or with a label of 800, because it's globally significant, I must send it to PE2 because PE2 is the destination. But there's an added complexity here. In this case here, in this example, we advertised the SID mapping with a setting that said perform PHP on it. So how many of you are familiar with PHP? Some of you? Okay. So it essentially, it stands for penultimate hop pop. And what that means is that you pop a label one hop away from the ultimate destination of it. It's an optimization. So don't worry about it too much. But essentially what we've done here is when a packet reaches P3 with a label of 800, it's going to look it up in its LFIB, and it says the out label is pop. Actually, just pop the label and send it out on the interface to PE2. So it's an optimization, right? So instead of swapping it for another label, we're just saying send it straight through to the destination because we know that's what it's. No, it's the destination. It told us it's the destination. So it's an optimization. if the PHP was not enabled for this, then you would have seen that the in label would have been 800 and the out label would have been 800 as well. So that's P3. Same thing happens at P2. So P2 receives that mapping of the SID, right? So SID of 800 mapped to the destination IP address, the loopback address of PE2. It does a similar sort of thing. It builds an LFIB entry that says in label 800, out label is 800, and the interface that I sent it to is the 1 to P3. So can anyone tell me why we did not do a pop here? Correct. Because what happens if it pops it? It'll go to P3 and P3 is going to go, what do I do with this? So P3 is going to be a bit lost. So we don't do that unless you're directly connected to the destination, right? So similar thing happens here at P1. P1 is exactly the same as P2. Incoming label of 800, outgoing label of 800, send it on that interface. PE1, a little bit different because PE1 is the ingress. So what PE1 is going to do is it's going to put an entry that we call a FAC to NHLFE kind of entry or an FTN table. I don't want you to get lost in all the terminology. Don't worry about that too much. Essentially, what it says is, if I get an unlabeled packet, a native IP packet, for example, that is destined for PE2, right? So if a packet is destined for PE2, put a label of 800 on it. So it's pushing a label, right? Ingress LERs take native packets, unlabeled packets, they label them. So that's an ingress LER, that's an egress LER. All of these routers, P1, P2, and P3, are LSRs. So what they are doing is just swaps. So they're not doing anything fancy. So the different, I guess the special processing is at P1 and at PE2, right? So a packet comes in, it labels it. So few observations. Once again, just to emphasize, there is no LDP here. There is no RSBTE. You've advertised the label using ISIS or OSPF, okay? They're both supported now. There's no dramas with that. Okay, so let's see how this works. So you've got the LFIBs here. Now, a packet comes into PE1, and PE1 looks at the destination of the destination address of the packet. And let's just say it's a BGP enabled network, right? It could be many things, but let's just say PE1 does a lookup and it says, hey, the next hop for that is PE2. So I've got to send this packet to PE2. Now, remember what we said was that what we're actually doing here is tunneling the packet. Now, what does a tunnel mean? What does a tunnel mean in the context of MPLS? What do we do to a packet to make sure it gets tunneled? Do we dig a tunnel? What do we do in an MPLS network? We put an MPLS label on it. You put an MPLS label, that's like tunneling your packet over it. So what PE1 is going to do here is look up that destination, which is PE2. And it'll say, okay, this is a native packet. Let me look in my FTN. It looks at its FTN, where it says that if the FAC stands for forwarding equivalence class. I mean, this is a long term for something that just is a prefix, okay? So let's just think about it as a prefix. So it says P2, then put a label of 800 on it. And this is an instruction to the network that says, if you see a packet with a label of 800, the semantic is to send the packet to P2 via the shortest path. So it pushes a label of 800 on it, on the packet, right? It sends it to P1. What's going to happen to P1? Same thing. It doesn't, well, not quite the same thing, is it? It's a transit LSR. So it will be doing a lookup in its LFIB. So it comes to P1. P1 looks at its LFIB. Okay, incoming label is 800. That's a top label. In fact, that's the only label. It looks at it and it goes, in label 800, my out label will be 800 as well. And the interface that I have to send it out on is the interface to P2. So it swaps 800 for 800. The packet looks exactly the same, but there's been some stuff that's happened there, right? It has been swapped, but it looks exactly the same. Same thing happens at P2. It looks it up, 800 to 800. P3 is interesting because we've got PHP happening there. So when it gets to P3, it looks up 800 and it goes, hey, I've got to pop it. So it pops the 800 and just sends the bare packet to PE2. Did everyone get that? This is crucial. This is the simplest example, but if you get this, you'll get the rest of it. So you better make sure you get it because we've still got another 100 minutes or something. So, it'll be a very boring 100 minutes if you lose me now.
If it doesn't run the solid mounting,
to PE3. So the question is, if PE1 was connected to PE3, and are you saying the PE3 is directly connected, and it's not running segment routing in the destination? Yeah. So okay, if that was the case, then if it'll do a lookup for it, and some of it's implementation dependent, but essentially the lookup will be a next hop of PE3, right? So remember, there's a whole resolution of next hops happening. So in this example, packet comes in, destination is PE2. Now you've got to find out how to get to PE2, right? That's a recursive, that's a resolution process. And in this case, it happened that it said, you know what, you've got to use segment routing. But if PE3 is not using segment routing, then the lookup is results in there being no tunnel. So it'll just get IP routed. Yeah. Yeah. Correct. And if you can't, then it'll fall back to whatever it is. And these things are configurable. On different implementations, we have different ways of saying, hey, give priority to segment routing or RSBTE or LDP, because they could be, all of this could be running together. And you could have in this network here, you could have a label for an LDP label for P2. You could have an RSBT tunnel to P2. You could have a segment routing tunnel to P2 as well. So you'll have to configure your router, say, hey, if you have all of these, this is what to use. And if you have none of these, then maybe fall back to standard IP routing. Does that make sense? Okay. Now, before I move on, I just want to make sure that you guys get this. So how would this have looked in a LDP network? What would have been different in an LDP network in terms of the labels and so on? Anyone? A stack of labels? Not necessarily in an LDP network. The labels would have changed at every hop, right? So what we got here is out label 800, in label 800, out label 800, in label 800, out label 800, and so on. In an LDP network, they would have been different because they were locally significant, right? So they would have been different. Now, the other thing is that even though the labels are the same, we're still doing a swap operation at each of these points. It's just that we're swapping a label value with an identical label value. But that is a very important point because that means that you're using the exact same MPLS operations that you had without segment routing. And that's a very important point. So you can use the existing data plane here for it. Yeah. Okay. Everyone cool with that? Any questions?
It's probably just a curiosity question.
No, sure.
Yeah, because the SIP is included in the packet.
Yes.
It's part of the label. What happens? Does it really change the 800 in the packet during the swap, or it's just?
Yeah, it does.
Oh, okay.
It does.
Does it change the packet?
No, it does. And that's actually, that's a good point, because that's exactly what I'm trying to say here, that the mechanism stays same. That there is no mechanism in an MPLS network where a packet goes in and it comes out without a change, right? There's no operation such as that. It's always getting swapped at every MPLS hop. It's just that it's getting swapped for the same value. Yeah. Anyone else? Any questions? Okay, I'll keep moving then. So, the other key point that I want to make now is around state. What is the state that we are holding in this network? How much? By advertising this SID value of 800, what state have we created in the network? That's state, right? That's state. Alpha state. That's a state. That's a bit of state here. That's state. That's state. The only state is associated with, in this case here, just the node SIDs and the LFIB entry for it. Okay. Now, if you had 300 tunnels here that were being routed between P1 and P2, same path, would the state increase? Would there be more entries in the LFIB if you had more tunnels? It wouldn't. Because remember, in a segment routing network, there's only 2 bits of information you need in order to route a packet: the node SIDs and the adjacency SIDs. The number of nodes in a network is not increasing as you increase the number of tunnels, right? You could build many different tunnels, different paths, but the number of nodes in the network remains the same. And that's the beauty of it, right? Once these LFIBs are populated, that's it. It stays that way. You can create as many tunnels as you want because the state is in the packet itself. And so, that's what we mean by no midpoint state. So in fact, it should be more correctly, no midpoint state associated on a per tunnel basis, right? It's these global state, which is the node SIDs, but there's nothing that is instantiated on a per tunnel basis. Okay. Right. Okay, so the SID values. Remember, I said that it's ideally you want to have the same sRGB, right? So when you have the same sRGB, you can have the same SID values. So let me just go back to this. Why does this work? This works because all of the nodes have an sRGB, which includes the value of 800. What if P1 here had an sRGB that was completely different? That was like from 1000 to 2000. Would this have worked? It would not have worked because that 800 value is outside of that range. So that would not have worked. So we have to deal with a situation when that happens. Now, in this scenario where everything is the same, we can talk about absolute SID values. When I say absolute SID values, I mean a label value, right? And that probably won't make any sense right now because we haven't talked about indexes. But for now, just accept that when I say an absolute SID value, it's the actual label value, right? So let's look at another example. Now this example is important because I use this in the rest of the tutorial as well. So this is a little, it's got a little bit more information. It's more real world in a way. So what we've got in this network here is we've got 2 PE routers, P1 and P2, and you've got 4 P routers, P1, P2, P3, P4. Now connected to these PE routers, we've got CE routers, right? Customer edge routers. There's a prefix A connected to C1, and there's a prefix Z connected to C2. So this is a VPN kind of a construct. So on P1, we would have a VPN constructed. This VPN has CE2 as a member, right? So it's participating in that VPN. So it's a very simple network. So in this example here, what we say is that, let's just say P2 is configured with a node SID of 600, which is advertised by the IGP. It also has the VPN service configured. And in this case, let's just assume it's an IP VPN service. We're using multi-protocol BGP, okay? So RFC 4364 kind of VPNs. And for this particular VPN service, P2 is advertising a label of 910 to PE1, okay? So that's the VPN label for it. So let's look at the scenario here. On PE1, because PE2 is advertised, its SID will create an entry there in the FTN that says if the transport FAC, so transport, I mean the infrastructure, prefix is PE2, they put a label of 600 on it, right? That's a node SID for PE2. And these are your intermediate nodes where in label 600, out label 600. Very simple, similar to the last example. It gets to PE2, out label is a POP. But this is a slightly different scenario where you're configured a VPN. So every packet will have 2 labels. Right? When you're using a VPN, you will have a minimum of 2 labels. The inner label is one that identifies the VPN that a packet belongs to. And the outer label identifies the node that is a destination of that packet. Okay? So the outer label gets you to the destination. Once you get to the destination, you get rid of the outer label, you pop it, you look at the inner label, which is what we call the service label. The service label will tell you which VPN it's a part of. If you don't have the service label, you have a problem. It's not going to know what to do with it. So you need to have those 2 labels because you get multiple VPNs, and VPNs can have overlapping IP addresses. So you can't just expose the packet and route. There'll be total confusion. So we need that. So that's what I'm trying to show here as a more realistic example, right? Okay, so what does that mean? Same example. We've advertised that. A packet comes in from CE1 into PE1. The destination address of the packet is Z. Where's Z? It's here, right? Now, the VPN context on PE1 will have a routing table associated with it, a virtual routing and forwarding table, a VRF. In the VRF, PE1 will look up the destination address Z. And what it's going to find out is that Z is connected via PE2. Okay? So it's got 2 bits of information. It knows that it's part of a VPN, and it knows what is the next hop for it. What's the next hop for it? P2. P2 is the next hop. So what it's going to do now is it'll take the packet and it'll do 2 things. Firstly, it will push a label for the service. Remember, we advertised label 910 for the service. So it pushes that onto the packet. It does that first, right? So the bottom label will be the VPN label, the service label. It will then push the label to get it to the next hop, which is PE2, which is label of 600. The packet's going to look like this. 600 on top, 910 in the bottom. And we know it always routes on the basis of the top label. So P1 will send it to P3. And if you recall the LFIB, 600 to 600. See, now all of you understand this now, aren't you? So this is all, we're in sync here. So I can speed up a bit. So 600 to 600, it gets to PE2. And this is where things get interesting. PE2 will first pop 600. Once it pops 600, what's going to be left is 910, right? So look up the label 910 in another table. I'm not going to go into the details of that just to keep it simple, but look it up in it's essentially you could say it's an LFIB as well, right? but the entry in the alphabet will say this is part of a VPN service. So by virtue of that, it knows which VPN service it belongs to. And it knows that it's the VPN service that C2 is connected to. And the next hop is associated with C2. So it sends the packet out to C2. Right, so that's how it works. Does that make sense? Anyone have any doubts at all? Okay. So all very, very simple. Quick question. Are we using PHP in this example? Anyone? It's yes or no. So 50% chance you'll get it right. A very conservative lot here. Come on, guys. Yes or no? Anyone? Are we using PHP in this example?
Yes, PHP.
PHP, yeah.
Yes.
Penultimate hop pop, are we using it? You're saying yes? Okay. Anyone else think is right?
I mean, like at the edge, we are using yes.
No. So actually, we're not, because the penultimate hop is this pop is this link here. So if you are using PHP, we would not have the 600 on it.
But at the end, like on the P2, like we're using yes, like popping.
No, we're popping, but that's not PHP, because the PHP is on the penultimate hop. So one hop away from the ultimate hop. But then the P2 is the ultimate hop. Yeah. So follow-up question, would PHP have worked in this scenario? It should work. Yeah, exactly. So, yeah. Correct. Exactly. So in case you guys didn't hear that, yeah, it would have worked, because what we're doing here is actually we are popping 600 on P2. P2 already knows it's 600. It's redundant information in a way, right? You're telling P2 something it already knows. Like, dude, you're 600. Yeah, okay, I know I'm 600. And then it's looking at 910. The important thing here is the label of 910. So we could have gotten rid of it and it would have still worked. But anyways, for the sake of simplicity, it's not using PHP. Okay. So how are we going for time? Okay, we've got 10 minutes. So let me give me a second, guys. See, I'm not sure I want to go into the indexing here. Yeah, you know what? I think I'll skip the section on indexing. It just I find it a bit. If anyone's interested in that, we can chat about it later. So indexing is a solution used when we have sRGBs that are different on different nodes. But I will skip that for now. Yeah, absolutely. So are they already there? Can someone check? They're not there yet. Yeah, because I uploaded around 12:30. So yeah, obviously it'll probably get reviewed, I imagine, by someone before it. They should be there shortly. Okay, so that was all about node segments, right? So now we'll look at adjacency segments. So adjacency segments identify adjacencies or links in the network. And typically the adjacencies are your IGP adjacencies, right? Now, there's a big difference between adjacency segments and node segments in the sense that node segments are globally significant, but adjacency segments are locally significant. That's because you don't really need to advertise that information. Well, I mean, you do advertise that information, but it doesn't really need to be globally significant. The value of that is only something that makes sense to the node that has it. Okay, so there's no need to use a globally significant address for it. So essentially, what that means now is that if you take an example, right, where AB is the node SID of a particular node. So let's just say AB. There's some sort of a number, and then ABC is a number that is an adjacency SID that is associated with that node. So now if we send a packet to this node with those two SIDs, AB and then ABC, AB will be on top, ABC will be next. It gets to a node, it looks at AB, and it goes, oh, this is mine. So I can pop it. It'll pop that label. It'll look at ABC. And when it says ABC, it'll look up that label in its label forwarding information base, right? And it'll look there and it goes, okay, what I have to do here is send it out of a specific adjacency. So when it sees an adjacency SID, it's not doing any sort of lookup from a address perspective. It's just doing a lookup in its LFIB and it's telling it, send it straight on this interface. Don't do anything else. Just send it out of this interface. So that's really what an adjacency SID does. So, I spoke about how to fully specify a path between an ingress and an egress router. Just specifying nodes is not sufficient. Why is it not sufficient to just specify the nodes along a path? Anyone? Why do we need more information than that? Think about it. If you want to go from A to Z, and you got a bunch of nodes in the middle, you could just say, hey, go to node 1, node 2, node 3, node 4, node 5. But that may not be sufficient. Why? Because you could have multiple links between nodes. Between node 1 and 2, you might have 10 links. So you want to have that ability to more explicitly specify which link is taken by the packet. So it's important to have that level of information as well. So this is where adjacency SIDs come in. Okay, so all segment routing routers advertise this adjacency SID information in the IGP as well. Just like we do with the node SIDs, we do it on the IGP as well, except that they have no locally significant SID values. Okay. Right, so let's look at an example here. So my network's growing a bit bigger. I've added a few more nodes here. So in this case, once again, we've got P1, P2, and we've got 6 P routers in the network. Now, all of these routers have node SIDs associated with them, right? You can see them. We've configured them. Node SID 100 here, 800, and so on. We've also got a few adjacency SIDs. Now, in a segment routing network, there'll be an adjacency SID associated with every adjacency. Now, for the sake of like keeping this diagram a bit manageable, I've only labeled a few of these adjacencies. So the adjacency between P1 and P2 has an adjacency SID of 1001. Between P2 and P5, 1007. P5 and P6, 1003. Okay. Now, all of these links would also have adjacency SIDs. I'm just not showing it here. The second point I want to make here is that in this network, or in this example, all the links have an IGP metric of 10, unless it's indicated otherwise. So this link here has a metric of 100. Okay. So what we want to do is we want to do some traffic engineering here, like we said. Like the whole point of this was so that we can do some interesting traffic engineering. And let's say your manager comes to you and says, hey, I want to take this path because it's cheaper or something, right? And you go, oh, that's a problem because my metric is 100. How can I route traffic this way? You could change the metric, but it's probably not a good idea. In a production network, if you want to hang on to your job, yeah. So I probably will not change the metric, but you think, how can I do some traffic engineering? So that's the path we want to take. And this is where adjacency SIDs can come in very handy. So what you do is you put a stack on it that looks like this. Now I want you guys to have a look at this and say, what is it actually doing? It's completely made of adjacency SIDs. I mean, I've taken a little bit of a shortcut here as well. But essentially what it's saying is P1 will have a next hop label forwarding entry that says, for this packet, send it out on the interface to P1, right? So you can see that, is there a SID for P1? Do we see a node SID for P1 in this? No, it's an optimization because we've got a entry in P1 that points directly at P1. So there's no need to have a label or a SID in there. Okay, so it gets to P1, right? The active SID or the active segment is 1001. Now, is it this one here? It's the top one, right? Because it's locally significant, right? I've done it on purpose. It's just to confuse everyone. No, for a very good reason, to show that these are locally significant. So the active SID is 1001. It gets to P1. P1 has an entry that says, if I get a SID of 1001, I'm meant to send it straight to P2. That link on that adjacency to P2 without doing any logos prefix match or anything. So it gets it, it pops, right? It's done its business. It pops it, sends it to P2. Now the active SID is 1007. It gets to P2. P2 does a similar thing. It looks at that and it goes, oh, the adjacency that I have to send it out on is the one to P5. So it sends it out to P5. Now the active one is 1003, all right? P5 looks at it and goes, oh, that's that adjacency to P6. It strips that, pops it, sends it to P6. P6 has an adjacency SID of 1001 that takes it to node SID 800. So it pops that, sends it to PE2. So you can see that, whoops, that kind of achieved what we wanted. It sent traffic over this link. Now, this is where we've got 60 seconds before our break, and I think I'm kind of on time here. But let's see if you guys can get creative here. Can anyone tell me any other ways of doing this with segment routing, like by using node SIDs or adjacency SIDs or some other combination? Can anyone think of any other combination that would allow me to follow this path? Okay, so SID to P5. Okay, that's one. And then adjacency to P6. Yep. And then to P2. Okay, so we've got one response here that says, so we put a stack that looks like this. We put the node SID, which is 600 for P5. We put an adjacency SID of 1003, and then we put an adjacency SID for P2. Yeah. Okay. So let me reiterate. So sorry, and your name there, Surasit. Okay, where are you from? In Thailand. Okay. All right. Thanks, Surasit. So Surasit, who's my assistant here today, has volunteered this answer. So he said, what we could do here, alternatively, is go P1 on P1. We put a label of 600, which is the node SID for P5, right? So the top one here, 600. And then we put an adjacency SID of 1003, which will take us to P6. And then we put a node SID for P2. Does anyone think that's correct? Is that, whoops. Anyone think that's going to work? Sorry, say again. By doing this, by what he's saying, by doing this P5. Okay. Yeah. Yep. Right. Okay. So that's good. Anyone else have any observations? Yeah. Good point. Right. Okay. So some good responses here. So Surasit, so basically what you suggested is not I think it still meets the requirement because the requirement is to use this link here, right? Except the path will be different. The path that you suggested here, let me get my laser pointer out here. We'll go P1 to P5 because that's the shortest path. Remember the semantics. What is the semantics of a node SID? Take the shortest path. Beautiful. So it gets to P5. Now, P5, there's no way you can use node SIDs here, right? Well, you could use node SIDs, but well, actually you can't use, there's no way you can use node SIDs in this environment, right? If you want to send traffic to P6, the only way is to use the adjacency SID. Because, you know, if you use a node SID for P, yeah, exactly, it'll go around, yep. So if you use, so say use P5, a node SID, and a node SID for P6, then it's going to go up this way. If you said P5 followed by P2 followed by P3 followed by P, I mean, none of that's going to work. So adjacent SIDs are important because it can bypass the shortest path, right? It forces you down a certain path and then takes you here. So this is great. And we might stop here because I think it's is that break time, 4 o'clock? I think it is, yeah. So thank you very much. We'll be back at 4:30 for the second half of it. There's a few more. I'm running a little bit behind. I'll try and catch up after the break. So enjoy your coffee and we'll see you in about half an hour. Yeah. Yeah, it doesn't get it. It could happen. It could happen. This is a special case.